So today what I'd like to talk to you a little bit about the interplay between statistics and AI. We're going to talk about how statistics can perhaps, statistical insights can improve AI processes. I would like to start with some recent work. So I actually do work on pre-training, which is a bit surprising for someone in academia, because pre-training is so expensive. But with my group, we've been really, and this is really the work with a fabulous grad student, Zhitong Yang, from Stanford University. We've been really interested in these scaling limits. So I don't think I need to tell you that as we get more data, performance of LLMs get better and better. And so this is sort of pictured on the left. You give me more data and things will improve. And at the same time, it seems that we're going to hit a scaling wall. It's because, just simply put, we're just running out of data. And so you don't have to take my word for it. You can just take the word of Ilya Sutskever. He gave a very famous address at NeurIPS in 2024, last year. And his claim, and I just quote from him, that pre-training as we know it will end because we're just running out of data. It seems that we have exhausted all the fossil fuels of pre-training, which is just tokens that were generated by humans. And so according to Ilya, things will change. They will have to change. And that's what I want to discuss a little bit. So my connection with statistics in this first part is not super strong, I should say, except that, of course, pre-training follows the principle of maximum likelihood, perhaps the most important quantitative idea of the 20th century. Let's try to imagine a world without maximum likelihood. It would likely be very different. And so what we try to do is, so basically, maximum likelihood, we want to train a transformer to make the likelihood of documents we see on the internet as likely as possible. But now we're running out of documents, so we're going to try to extend this pre-training beyond the scaling limit. And we're going to do this by synthetic data. And here, of course, you're going to see a proposal that changes from a lot of things you would actually hear at top tech companies, where you might hear things like, no, the frontier is R. We are believing, at least in this project, that there is a lot of untapped resources that we have not explored yet. And I would like to just show you a little bit of thinking in this area. So we're going to start with a simple idea, which is synthetic continued pre-training, which we published last year. This is with the group of my colleague Hashimoto in CS at Stanford, and then we'll talk about the most recent work. So maybe I'm going to use an example where, I don't know if you played with ChatGPT, and I assume everybody does. I'm teaching a large class in linear algebra right now, and I'm having a little bit of a trouble, which is whenever I give a problem set, ChatGPT seems to know the answer. But if you give ChatGPT a problem in quantum gravity, then the answers are really no good. And one of the reasons is quantum gravity is a very niche subject, and so you don't have a lot of documents, and so the model is not really able to learn quantum gravity. Perhaps also quantum gravity happens to be a bit harder than just computing the SVD of a 3x3 matrix. But also what we have is we have businesses, and they are trying to use language models, but these models don't know anything about the data they own. They've not been trained on the data they own. So these are typical niche applications. We can think about a niche application in physics. We can talk about a niche application in a company. And the problem with the company is that, again, the model doesn't know anything about the customers of that company, the data of that company, and anything like that. So the question is, how can we teach the model knowledge from a niche domain consisting of a few source documents? So, for example, a few quantum gravity papers, or a few documents that your company might have that were not in the pre-trained corpus of OpenAI. And so, what we're going to do is we're going to say, well, we're going to try to achieve this by actually generating a lot of new synthetic documents, so that we're going to try to teach the model what your niche domain is about. And we're going to do this continuously by generating new text. And then you're going to see performance on actually real benchmarks. So the method is very, very simple. So the question is, how do you generate new text that is diverse? So of course, a lot of people have tried to rephrase quantum gravity papers, or if I take my other example, or linear algebra papers, or textbooks, but that is not really helpful for the model. With simple rephrasing is not really helping the model. So what we're proposing here, and I'm going to use linear algebra as an example, because I think we all know linear algebra, and we know less about quantum gravity, but I'm going to use linear algebra as an example. Here is a kind of synthetic token that we're going to generate. We're going to generate a lot of synthetic tokens. You're going to see on the next slide that we generate close to 600 billion new tokens, but not by asking the model to rephrase textbooks. In the context of linear algebra, what we're going to do is we're going to build a knowledge graph. And the way it works is we ask the model to read about linear algebra, and then we're going to ask the model to name entities that it has learned while reading. So it's going to say, well, I've seen something like an eigenvector, and I've seen matrices, and I've seen an SVD, and I've seen a least squares problem, etc., etc. We're going to then ask the model to produce tokens to describe these entities. It's going to, well, the SVD is a factorization of a matrix of the following kind, and this first problem is the optimization problem with the following structure, blah, 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 blah. Then we're going to take pairs of entities and we're going to ask the model to actually tell us about how they relate to each other. So for example, the model might say, well, I might use the SVD to solve a least squares problem. And then sometimes when pairs are quite promising, we're going to ask the model to actually tell us something about triplets of entities and how they relate to each other. So basically, we're generating a lot of tokens, not by asking the model to rephrase the textbook, but just by extracting concepts, describing those concepts, relating them to us. And in doing so, it generates a lot of new tokens. And the surprising thing, the thing that we're surprised to see, is when you follow a path like this, you take a model that is actually quite poor. And so this is what I'm trying to take here. It's like, oops, I think I have this kind of thing. This is, it doesn't work, so maybe I should point it here. Can you see it? Okay, no, you cannot see it. So this is a gadget that my fantastic student Ziton gave me. I think it works if I point a camera at a TV screen, but not at a screen like this. Anyway, you take a model that is quite poor, and so you give him a standard benchmark accuracy, and so it's quite poor. And in fact, you know, like I cannot access GPT-4. I don't have the resources to do it. In fact, I cannot even modify their weights. And so GPT-4 is quite accurate. The model we started with, which is actually Llama 3 8B, is not doing so well. That's why GPT, as we know, is better than Llama 3. But then we give it the synthetic tokens that we produce ourselves. And what you can see is you can see the performance improvement as the number of synthetic tokens grows. And so all of a sudden, it's going to go above GPT. And of course, it's going to plateau at some point. I think one of the reasons this graph does not further extend is that we reach a limit and the model does not improve. And you can see a quite serious improvement. So being able to generate diverse tokens seems to improve models quite a bit. I want to present now a new idea, which actually I like best, which is very new, and this is a joint work with a team at Apple. It's the same team as before, but now a team at Apple because, well, first they have great ideas, but also because they have resources that we need to kind of carry out this kind of work. So, all right, so I'm going to propose a method that is going to involve a form of very weak supervision that actually language models do not exploit at the moment. And this is the fact that, you know, if I try to kind of give you the spirit of this work in 1 second, I would just say that right now, you know, as you know, language model is next token prediction within a document. It exploits correlations between tokens within a document, but it does not exploit them across documents, and that's what we're going to try to do. We're going to introduce a form of weak supervision where we're going to try to understand correlations within across documents. So how is this going to work? So you give me a bunch of documents, and we use a famous data set called DCLM, which is quite big. You know, it has a lot of tokens, 500 billion tokens after cleanup. And then we're going to use an embedding where we're going to map these documents into Euclidean space. And then you see a picture and representation of these documents. And some of them tend to cluster together, and some of them are a bit farther away. So for example, a cluster is, I don't know what relates to Harry Potter. Another cluster is, the famous transformer paper from Google, and quite related would be a PyTorch implementation of that paper that you'll find on GitHub. Perhaps a thing that is more isolated is my paper, which is not as known as a transformer paper, a novel that is not as known as Harry Potter, and stuff like that. So we're going to embed, and actually how you embed when you have so many tokens and so many documents, it's a subject in itself that I'm going to skip, because you have to do this efficiently, and so I'm going to skip that for a second, but you embed. And so then you get with pairs of documents that are close in embedding space, and of course they're related. So here are two pairs of documents that are embedding found very related, and one is about the history of Iran, and the second is about, well, if you were to travel to Iran, which historical site should you go and visit? Okay, so we find pairs of documents. And now I think the novelty starts, which is that, by the way, a document can have several neighbors, can have several paired neighbors, and now the novelty starts, which is we're going to take the current language model. In our case, it's Llama 3 again, because we're going to try to change its weights. So we take Llama 3, an open weight language model, and we're going to ask it, we're going to start at Llama 3 with a checkpoint model, and then we're going to ask it to generate the second document from the first. All right, so we're going to ask it to generate D2 from D1. Now D1 may have multiple pairs, but we're going to ask, we're going to keep on training the model so that the model knows how to write the PyTorch implementation of the transformer paper, just from the transformer paper. That's what the idea is. Okay, so we're going to fine-tune the model, and then we go back to the database, and we take my paper, which is not so well known, does not have a lot of, and we say, what would be a sister document to that paper? What would be the D2 for Emanuel's paper? So maybe it's going to write a Python implementation of that paper. Maybe it's going to connect it with a paper that some of you are working on, etc., etc. Okay, so now we generate what I want to call in red Internet 2. We have Internet 1 in black, and then we generate in red Internet 2. And now you have a much bigger corpus of documents because you can do this at will. And so you can generate a lot of new documents. And we're going to join on the real and synthetic data. So now we're going to bring back this second internet in our original pool of documents, and we're going to fine-tune the model, just do an X token prediction on this thing. Now, what's very interesting is how do the synthesized document look like? And so I give you an example. I don't know if you can read my screen, but on the left you see the original document. It's a document that does not have a neighbor, and it's a first-person guide to the coffee house in San Diego. And then we look at, okay, now please generate a synthetic document that goes with it. And then the first time we try, so of course the temperature is not 0, so we get randomness each time. And so the synthesis 1 sticks to the same topic but shifts towards an expository essay on espresso machines, bean quality, with little mention of coffee shops, which was the theme of the first paper. So it starts to talk about espresso machines, etc. So it's not rephrasing the first document. The second is kind of interesting. It says, no, it's going to take a completely different point of view. It adopts a more like promotional, comparative style, linking the San Diego coffee scene, which was the subject of, with the New York coffee scene. And it's going to praise the Café Lestat in a way that departs from the original balance assessment. It's like far more comparative and a bit promotional. And so that's what you get. You don't get a rephrasing, you get things that are genuinely distinct. All right, so now you have your second internet in red, and you're going to say, well, I'm going to train on this. I don't think we're real data. Of course, the quality is not the quality of real data. I'm going to show this in a minute, but you train on this. And now how do you show that you do something good? Well, you're going to run a very, very controlled experiment where you're going to have a bunch of benchmarks that perhaps you know about. And then you're going to have comprehension, understanding benchmarks. So basically the top is like I'm trying to assess the likelihood of documents I have not seen. And the second is I'm trying to do well at science and reasoning questions and so on. And so in black, you see the performance of the bedline for 2 scales. So we tried 200 billion tokens. And so maybe during the hour, I can tell you how much this paper costs. It costs a lot of money. And then we even have a terascale. So we have to pre-train on things of that size. And so you have the baseline. And the baseline, what it's doing, it's just doing gradient descent on the document it has. And so the experiment is controlled so that the compute time that you spend for each method is the same. All right? Then, of course, we have an Oracle baseline, and the Oracle baseline has a lot to it. The Oracle baseline has 20 times more original data than you do. And so, of course, it does better than the baseline. And so you see that an improvement. And then in red, you see our stuff. So everything is well controlled. We spend the same amount of compute and so on. And what we find interesting when we discuss this among ourselves is that you can get 40% of the improvement that you would get if you had 20 times more original data. Now this is not the table I wanted to see. I talked to the team. I said, I want a table to say, what is the effective sample size? Like, to get the same performance, it's like, you would need to see how much more high quality data, real data. And that's what I've been told. Yeah, this is the table we should have produced, but we cannot reproduce it because of the cost or so. Okay. Now here's another thing which I find interesting, which is that as we kind of train this new model, so you have the 3 methods that I've discussed before. You have red is us. We have the Oracle that has access to a lot of 20 times more original data than we do. And then we have the baseline, which is also going to just reuse a lot of the same data. And so you can see that, the beginning, the baseline and the Oracle, well, they don't do a lot of compute, so you do stochastic gradient descent, you call batches, they're sampling from the same distribution, so they start to improve the same. But then they start to diverge. They diverge because essentially the black line is running out of data. So it's seeing a lot of the same stuff again, while the Oracle sees new data, and so its performance continues to improve. Now we can compare this with the red line. The red line starts worse, and the reason it starts worse is at the beginning, we have in the mix our synthetic document that are not as high quality as the real documents, so the performance is a bit worse. And then it starts and then it crosses the black line because it says, I have actually a lot of useful data that you do not seem to have, and so for the same amount of compute, I can all of a sudden do a lot better. All right, so this is encouraging, and I've been told that some companies are using this. Okay, so I think this is really like something I think I heard Jan LeCun said, which is that, I think that a lot of what we can do today is because we do self-supervised or a form of very weak self-supervision. It seems that this is getting into trouble because we're going to run out of data. As I said at the beginning, people are looking at this differently. Says, oh, we're going to do a lot of strong supervision with a lot of RL. That's not what this is. This is a bit different. It said that we can propose a very weak form of self-supervision that is far weaker than actually next token because it's trying to extract knowledge across documents on the internet and build from it. All right, so this is the end of my first part, which was essentially like, when we think about AI, and if we think carefully about what AI is, data comes in. So I told you a little bit about the kind of data that we could feed into AI. Then there's the process itself, and then there is the outputs, and what are you supposed to do with the outputs, which we're going to start to discuss now. So this is where I'm going to go a little bit more about statistical thinking. And I think that this thing where we put data, we do some stuff, and then we cure cancer is oversimplified. And I want to talk to you a little bit about the complexities of this chain. Now it's oversimplified. I have to say, I live in an environment where there's a lot of hubris around what we can do with AI, and I think we need a bit of science here. Okay. So data collection, I've talked to you a little bit about this. We've done a lot of other works on data collection and how we can curate data to achieve certain goals, and what should we go into an AI system so that we can achieve good goals. I just talked to you a little bit about what we've done, but we've done other things. I want to talk to you a little bit more about data-driven discoveries and the field that is taking the field of statistics by storm at the moment, called AI-powered inference. And then we're going to talk a little bit about quality control, what to do when we get the output of an AI system, and we're going to need to use this output to do things of significance. So let's talk about AI-powered inference. So your team of your assembly of scientists, statistical thinking. So this is me wearing my statistical hat, has had a very, very, very important impact on our lives. For example, I will make the claim that along with medicine, the field has contributed to increased life expectancy by, I would estimate, about 20 years, and feed about 8 billion people as well. So we have enormous things to be proud of. And when I try to understand the effectiveness of a vaccine, I don't have a mechanistic model of how vaccines work. I just collect data, I make experiments, and then I try to do some form of inference, right? We must learn from data. It seems like a lot of things are very complicated to actually model with equations the way we used to at the beginning of the 19th and 20th century. So how are we sure about what we learn from data? Well, this is what, maybe you don't need a slide like this because you already know about this, but if I want to there's a parameter of interest, which is the effectiveness of a vaccine. The way I'm going to argue with the FDA is, well, here's a randomized control experiment, and I can certify with a certain probability, and it probably just depends on the sampling mechanism I use, is I actually toss the coin that the quantity of interest is within a lower bound and an upper bound. And so for us, for example, the quantities that we worked on a bit with now a different group of students with Kiana Azernich is, well, for example, an object of inference might be what is the level of deforestation in the Amazon right now? And that's going to be hard to assess. Actually, the Brazilian government is very interested in this question. They send trucks in the Amazon, as we'll see, to actually measure. As you can see, it's very expensive, and so can we do better with AI? Mine can be interested in the effectiveness of a vaccine, the side effect of a drug, and of course, if I just trust predictions of a machine about whether a vaccine is going to be effective, I might kill people. And actually, we've done it in the past. So, if you don't do things properly, if you don't apply the scientific method, so to speak, you can do a lot of harm to a lot of people. And it's not that we haven't done it. We have done it. So. All right. So what I would like to talk to you about in the next 20 minutes is whether we can leverage imperfect AI predictions to get gold standard results. So how much deforestation in the Amazon? Which fraction of food things have a certain property? How much has political sentiment in the media changed? Of course, I need to collect data to achieve these things, but collecting data and labeling this data is very expensive. Let's take the first example, and that's what the Brazilian government does, is they send trucks and they measure square inch by square inch how much of it has been deforested. Sentiment in media change, you can have people read the news article and do, that is expensive. The middle one is perhaps even more expensive. I have to make experiments in the lab and they're very expensive. And so of course we would like to use AI in lieu of real data. That's what everybody does and that's what everybody wants to do. So here's the setup. I've got some labels that I don't see. I have a lot of features, and so let's look at this Amazon example as a running example. I would like to know how much deforestation. So, if I could go across the Amazon and completely do a census of the entire Amazon, I would know, but that's too expensive. Instead, the way I can think about it is I have satellite images. Now, they're not measuring deforestation. But maybe they can help me predict or estimate deforestation, perhaps in a biased way. So what we're going to do is we're going to collect some labels, not a whole lot, little n. So in the next few slides, we're going to have a little n, which is the amount of labels you collected yourself. And you should think about this as small because very expensive. And then here, so you have a bunch of images for which you actually know the deforestation level. All right, and then we have a lot of images that survey the rest of the Amazon for which we do not know the deforestation level. And of course, it's going to be tempting to impute the prediction of your AI system about the amount of deforestation on what you haven't seen. But of course, what if it's wrong? What if it's biased? Right? Again, we want to do science. We don't want now, we just don't want to do, I did this because I can. All right, so we want to estimate the deforestation rates in the Amazon. And so we're going to produce informative but imperfect predictions for the stuff that we could not actually send our trucks to. We're going to train or fine-tune ResNet or some imaging model to actually learn deforestation from the few data that we have. Now, of course, it would be foolish of me to actually take this prediction and pretend it's real data, because it's not. But here's what you can do. So what we could do is we could pretend that it's real data and then debias it. And so I'm going to claim something that is a bit strange, which is that I'm going to take the average of what I would actually take if I thought that the AI algorithm was correct. But it is incorrect. In fact, it might be strongly biased. And then what I'm going to do is I'm going to subtract an estimate of the bias. And so by doing this, I'm going to get something which is completely unbiased. And then I can do a lot of math and statistics and show you that actually I can achieve what I'm going to get is the gold standard, which is what you would get if you had followed the traditional statistical recipe. It would have the same validity as if you had followed the recipe. So I propose we see this on one example. You can do this on a lot of examples of parameters of interest to you, but I'm going to just take the simplest one because it's a plenary lecture, which is the mean, so as not to get into detail. So the classical way of estimating the mean is you take a random sample and you just take a sample average. This is what you see on the left. And what prediction powered inference is about is, no, you're not going to do this. You're going to do something different. You're going to take the average of your predictions, which would be a wrong thing to do. But then you're going to add a debiasing term. And the debiasing term is essentially the difference between the label you observe and the prediction of your algorithm on the data part that you observe. And if you know a little bit of statistics and you want to compute the expected value of theta hat pp, which is the estimate on the right, then you would see that, well, it's actually what you want. It's a mean. So the two terms that are biasing actually cancel out each other perfectly. So it's unbiased. Of course, we know from undergrads the variance of the estimator on the left. What about the variance of the estimator on the right? Well, the variance of the estimator on the right, I'm going to ask you to think that, well, capital N is very large. I surveyed all the Amazon. Capital N is 100 times little n. So we're going to discard the variance of the first term. What really matters is the variance of the second term, but it's basically the variance of the variance in the y that your model cannot explain. So it's going to be much smaller. All right, so this second term is going to be much smaller, and so when your predictions are good, and n is much larger than n, this second estimate has much, much, much lower variance. And, you know, there's all the good stuff that I can do, all central limit theorem stuff, and the distribution is approximately normal, blah, 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 and so I can construct confidence interval and achieve the gold standard. And so you can do crazy things with this. So you can say, well, should I use AlphaFold to actually hinder your experiments? And say like, well, that you'll be surprised that there are papers in Nature and stuff that actually do this. They don't collect data. They just say, hey, AlphaFold did this. And we're supposed to believe the outcome. I think this is crazy. So what you can do is you can say, I'm going to have a little bit of data use AlphaFold to predict the rest, then do the stuff you see and get something that actually now is science and not just garbage. So this is a confidence interval using naive AI only, like you forget real data, you just use the prediction, it's completely off. I'm not sure what you can do with this, not much. People like to think they can do something with it, but I don't know what you can do with it. This is what you can do if the kind of confidence interval you would get if you only use your ground truth data. But by using both AI and the real data, you can get this interval that is actually centered in the right place and is shorter because it's like if you had more samples, because the variance term has gone down. Now, the way I'd like to think about this is that if we think about a classical statistician, this is your sample size. But if you use the method we're describing, it's like if you had a much bigger sample. And so your effective sample size, you think it's 800, but it's actually 2,000 because you used AI. And you actually sacrifice nothing because the type 1 error guarantees are still there. All right, now we can go a step beyond that. And we can say, but hey, why should I actually send my trucks at random locations? Maybe I should send my trucks where the model is really not sure about the level of deforestation out there. And so now we could even do this, use these kind of ideas to not just improve the estimate, but guide data collection itself. So, in words, what we should do is we should prioritize collecting expert labels where AI makes a mistake, etc. So what we're going to do is we're going to say, well, they are, if you think about, my Amazon thing, you look at your satellite images, and I'm quite sure like that there's not, it's just tree cover, nothing has been deforested. And then I said, this area I'm less sure. My estimates are not really good there. I just don't know what to think. So maybe that's why I sent trucks. That's the idea. All right, so when we're going to do this, we're going to be able to actually inform data collection itself and then use this on top of it, the stuff we've seen already. And so we're going to see this come together. What I just want to say is that at the end, we're going to get the gold standard. That is, as if I run a randomized control trial. So here's how it's going to work. We have our prediction from our black box. And now we have a measure of uncertainty. Suppose I could estimate, well, let's just look at the regression case where I'm trying to estimate the amount of deforestation. Suppose I could estimate, like, the error that my model makes, like the magnitude of the error. Well, if I could do this, then what I would like to do is to actually send trucks where I think my error is large and not where it's low. All right, so you can introduce a sampling policy that basically depends on the quality of your model for feature vector xi. And then you're going to sample observation according to pi of xi. The less certain you are, the more likely you are to be visited. The more certain you are, the less likely. Now, of course, this introduces a bias, but that's no problem. We're going to correct this in the formula. And so at the top, you have a new estimator, which now takes into account your sampling policy. It's going to visit data points for which uncertainty is high, less frequently data points for which uncertainty is low. And then again, if you have a bit of training in stochastic things, you'll realize that this is also unbiased. But now I'm going to spend less time actually going to Emanuel's door and see how he thinks about the next election. Because, well, I already know a lot about Emanuel. And okay. So this can be done sequentially. You don't have to do this in batches. You can do this sequentially. And so now you're just going to use AI to not only inform collection, but then use the predictions to it. So you use it twice. And then if you go back to my previous example, then you improve again. So this is what we see if I use AI to use predictions. Okay, that's good. And then now I use AI to actually go in the lab and make the experiments that are informative, for that I don't really know the answer already. Okay, and everything passes the gold standard, and now you have a much bigger effective sample size. So I hope this gives you an idea about how we can use AI together with statistical thinking to actually use imputation, but in actually a fundamentally correct way, not just making stuff up. Okay, now, this is a last instance of what I wanted to tell you a little bit about this series of projects, which is, and what if you don't have a goal yet? So the way I'd like to think about it is, all right, so you want to get an annotated data set, but it's very expensive because you're going to have human labelers or stuff like that. Can I sell you a data set where 99% of the labels are correct and maybe 1% is not correct at a much reduced cost? Because I'm going to outsource a lot of labeling to AI. But what we cannot compromise is a fraction of labels that are not correct. So this is what we're going to try to do. Now we think that we have some features I want to label. So for example, this can be patient, this can be their genotypes. Do they have this disease or not? And of course, diagnosing a disease is expensive. Like you have to go to the hospital, run some tests, blah, blah, blah. Okay, perhaps I have a model that predicts disease from genotypes and other types of environmental factors and habits that you may have, or your phone, or anything like that. And then I can try to make a prediction. And maybe what I would like to do is I would like to return a data set that, because I want to do science, I would like to understand which factors drive the disease and so on. But it's very important that at the end of the day I have a data set where perhaps everybody has been labeled correctly, but maybe a small fraction. And that I control. So what we're going to be very prescriptive on is the fraction of incorrect labels is under control. What is variable here is how much humans I'm going to involve in labeling. But the outcome is controlled. Okay. So we want to return a data set while correlating as few experts Y's as possible, such that, well, I don't know, yi equals y for 95% of the data set with 95% of. That's what we want to do. And so we have a method that does this. Again, it's using AI. It makes predictions about whether you have the disease or not. It has uncertainty scores about the quality of its predictions. And then it has a loss function. And the loss function is something that looks like this. You have a loss. I'm sorry that this cannot point. You have a loss. All right. Okay, so you have a loss function that you see. And then, of course, this loss function is monotone in the amount of work you ask humans to do. Because if they do all the work, your loss function is 0. And as you ask them to do a loss of the loss. So you're going to try to build an upper bound on this loss function. And then you're going to exploit the monotonicity of this loss function as a function of at what value of uncertainty do I need humans to take on. And then you're going to do some math, and you're going to end up with a rule. And that rule, but for those of you who care about stuff like this, this upper bound does not have to be simultaneously valid. That's the great thing about it. And so then you get a rule, and then you say by actually asking people to label above u hat, and just outsourcing to AI below u hat, you have a packed label data set. So I'm going to call this a packed label data set in the sense that almost all labels are correct except a few, and that fraction you control. Now, of course, the quality of the amount of work you can save humans depends on the quality of your prediction model. And so we have looked at a lot of data sets, misinformation on the internet, stamps of various news articles on global warming, media bias, and so on. And, I want a 5% mislabeled data set, and that's statistics, that's math, that's science. You get exactly 5%. In fact, I'm a bit conservative, but not a whole lot conservative. You want 5%, I'll give you 3.8, 4.5, 4.9. And then here you see the fraction of work you save. And of course, if you outsource ChatGPT, hey, ChatGPT tells me about media bias. Then in this case, I don't know, 38%. Now, what are you supposed to do with this if 38% of the labels are wrong? I'm not exactly sure. All right. And of course, your work in imaging. Imaging is an area where, of course, now the predictions are far more accurate because the signal-to-noise ratio is almost infinite. And And so when you apply these techniques to actually label data set, whether it's ImageNet 1 or ImageNet V2, second ImageNet instance, then of course now you can save a lot of and get very, very high accurate labeling. All right, and of course, if you were to just outsource the entire thing to ResNet, there's no way you would reach your 5% accuracy. Okay. There are many variations on these themes that we could explore. I'm just going to tell you what they are and maybe skip details, but we also live in an environment where you can choose your worker when it's, well, okay, so you can use a human, but if you don't use a human, and maybe humans are expensive, Gemini has a certain, you need to start calculating the price of inference, and ChatGPT, and blah, blah, blah. So the question is, well, these things have different costs, they have different accuracy also, and so is it possible to actually blend this with a router that would say, hey, I need to label X2. It goes where? Does it go to a human? Does it go to Gemini? Does it go to et cetera? Because my experience is Claude is better at coding than some other models. But conversely, Gemini is better at something, et cetera. And also they have different prices. And so what we've also built is we've built a router that optimizes the final labeling cost. What we cannot negotiate is the accuracy. What we're trying to do is bring the cost down as much as possible. And so maybe I'm not going to go through these slides, but these slides are supposed to convey that if you were to just take one language model alone, you have experienced a certain budget save. Maybe we could go cost directly because we have now API cost factored in. So you have a certain saving cost. And of course, you're more tolerant about the error, like the saving cost starts to be enormous. But by using these routing strategies, the saving cost is much, much higher. So there's a way of actually combining the accuracy of these agents, if you will, into a routing scheme that actually routes the labeling the correct way. Again, you are not compromising on the quality of the answer. All what you did, if you did a good job, you're going to spend less and less money. All right, so my takeaway for this part is that statistics alone is great. It's reliable but expensive. AI alone, not reliable, but powerful and cheap, and there's a way of trying to put them together. Okay. My last, do I have 10 minutes still? 10 minutes? Okay. Is about a more subtle topic now, which is how can we do drug discoveries? Can we do AI-powered drug discovery? I'll try to introduce a problem. I probably won't have time to discuss details too much, but again, maybe if I convey the flavor of these things, maybe I'll do something good. So, short story, bringing drugs to market is very, very expensive. And the reason it's expensive is, of course, that a lot of physical experiments are involved, right? So you have a bunch of candidate drugs, labs, and I should say before I get started that we did a lot of work with, I did work with Ying Jin, who was my student, and now at the University of Pennsylvania at the Wharton School of Business, but we also started a collaboration with Gen and Tech on this, so we're actually synthesizing new compounds as we speak. And let me just explain a bit the gist of this stuff. So you have a bunch of candidate drugs, and are they going to bind to a target or not? That's what you want to know. And well, to do this, you need to perform experiments, and that is very expensive. So that you can, after the experiment, you can prioritize high-score drugs, and then perhaps think about doing clinical trials and stuff like that. You go down the chain. But first, is this reverse transcriptase going to, stop the synthesis of the AIDS virus? So this is what you need to know, like how you're going to block a physical process or not. And of course, now we'd say, well, how about I use AlphaFold again? AlphaFold and its followers. I would like not to do physical experiments, use a prediction of algorithms to actually replace physical experiments. That's a promise. Okay, so I would like AI to use AI as an imperfect scoring mechanism to prioritize drugs for later development. That's the plan. So far, so it looks like this. You know, I have some molecules. I want to know whether they're going to bind to a target. And in this work, we use extremely sophisticated neural nets. I do not pretend to understand. I don't pretend to understand them. In fact, that's not my job to understand them. My job is to take whatever they tell me and convert it to something I can actually trust. So we want to make predictions. And if you look at papers in Nature and blah, you know, AI has potential to use this reality check. You know, what have we done that is so great in the last 10 years? Not clear. Okay. Because it's a tough problem. So here's the thing is like, I want drugs with a high binding affinities to a disease target. So which drugs are sufficiently active for me to be of interest? And if we think about this a bit as a machine learning problem, this is a problem. I have a pre-trained prediction model that predicts the affinity of a molecule for a target. So here X might be the sequence of amino acids of the drug. It can be the chemical structure of the drug. And then I'm going to use this very fancy neural net to predict whether they're going to bind to a target molecule or not. Y is a binding affinity. 0, 1, here's how you bind, or if it's real value, how well it binds to the target. And then I have some training data. So I have some library of chemical structure and activity scores, or affinity scores. And so these are the blue drugs. But I don't know if you've seen, I think DeepMind has released a library of 400 million drugs that we could potentially synthesize, and which one should we synthesize? Right, so I have now a lot of drugs that I could potentially synthesize, for which I do not have the activity scores, and I wish to explore that space now. Okay, and I think I can summarize a lot of the activity in this field by, well, of the drugs for which you do not have an activity scores, which one, can you tell me ahead of time, which one have an affinity above the threshold I determine? Now this threshold may not be fixed. It might be, you know, Emanuel, I already have a bunch of drugs, they have these affinities, you need to be at least 50% above that. So that is itself random, so it can be random. But what is it that we need to do as statisticians is to find those drugs for which, if I were to measure them in the lab, they would indeed pass the threshold that I was given without too many errors. And an error here is not mean squared. If it's below threshold, you're going to throw out to the garbage. So it's really very discrete, very 1-0 type. You lost, if it's below threshold, you lost a few hundreds of thousands or tens of thousands of dollars to actually make experiments that go nowhere. Okay, so this is a problem. And so what is difficult about this? Well, we need to quantify the uncertainty that AI thinks this drug has a high affinity. Well, should I believe it? Should I not believe it? And of course, we're way past Gaussian models and parametric models that we've manipulated for a while. And there's a problem also, which I'm going to discuss, which is that you have a tremendous distribution shift typically between those drugs for which you have affinity and those drugs for which, because you have, it's a bit like when you hire people, you have affinity for drugs that looked interesting in the first place. And this is a slightly different population than the drugs that I have not explored sitting on my computer. Okay? In the same way that, I don't know, Stanford students are not representative of Stanford's, we admitted, are not representative of all students in the US. So we have this problem as well. So I guess I was invited to talk to you about conformal prediction. It comes after 50 minutes. So conformal prediction is a way to evaluate model uncertainty, except it's not exactly what we want. So conformal prediction is a method to turn a point prediction, a prediction from an AI system, into a prediction interval that has good properties. And those properties are that when marginally, and that's very important that we understand this, marginally, when I take a new test sample, xn plus 1, and I construct its prediction interval, the true label will belong to this prediction interval with probability 95%, let's say. Okay, but it's very important to understand, when I take a new test sample at random, this is what will happen. Okay, so it covers 95% of the outcomes, no matter the prediction model. That's what we've learned from conformal prediction, and it's absolutely a fabulous field. And so, you know, I could try to use conformal prediction, and conformal prediction would say, well, this is my target C, this is this green line. I'm going to find prediction intervals with the coverage that you like, Emanuel. Some of them will be on the left of C, some of them will overlap with C. And you know, we see two of them for xn plus 2 and xn plus 1. They're on the right of C. They look to be good because my predictions have uncertainty in them. They are the right value on the right. So yeah, should I take these two drugs? And the answer is you can't do that. You cannot do that. If you do that, you're going to have a selection effect that is going to be very strong. And because you're looking at many, many things at the same time, it's like a bit like the monkey typing Shakespeare. This monkey has typed, and you see the beginning of Hamlet. Does it mean? That's a bit the problem with a very strong selection effect. And we cannot use this. So we're going to need new ideas, because if I were to actually do exactly what I said, I used conformal prediction, I was assured that it works, and when I actually try to use it, it doesn't work. And the reason it doesn't work is that the selected samples are not representative of the entire thing. And so there's a very different, there's a selection effect, a winner's curse, if you will, that takes place. You want 1% nominal error, and then you're going to get 30% after selection. So that's not good, because this is this well-known thing of the winner's curse, right? So we need to deal with that. All right, and so what we propose doing, and you might think, how are we going to use this? What we propose doing is, what we're doing with Genentech says, okay, we're going to use the predictions of machine learning. We're going to return a list of candidates to you that you should perhaps go and experiment on. And we're going to guarantee that out of these 62 drugs you're going to experiment, 90% are going to be fine. You're going to waste your 10% of your money, but 90% of them. That's what in statistics is called the false discovery rate, except in a very different context. But we want to control the expected fraction of wasted time or wasted money. So we want to control the fraction of false discoveries, things that you're going to go and experiment and that did not pan out over your total budget. So the company might be fine spending 20% of its budget following false leads, but it cannot afford spending 90% of its budget following false leads. It's going to run out of money. Okay, so we're going to try to use AI prediction and then we're going to try to put a statistical layer on top of it to prioritize those drugs that should go for experimentation in such a way that the fraction of money that you're going to lose is controlled, or time or everything. Now, I mentioned the distribution shift. This is something that you have to deal with when you're out there in the field. You don't have distribution shift if you prefer drugs, but in general you will. Okay, so typically the training set you have is not the same as the test set. Okay, so in reality we have distribution shift when you're scrolling, and you have this in a lot of different context, you might want to apply these methods. Okay, so what we're going to assume here is that I have two populations. A population that is, they're both unknown, by the way. I know nothing about them except data. Like there's no model of any kind anywhere. And then there's a population which is a test data that coming from a distribution Q. There's the training data for which I have labels that comes from P. What I'm going to assume is that the ratio between these two likelihoods depends on X only. Because for my drug stuff, it is exactly what happens. Like whether something binds to a target does not depend on whether, it depends on your chemical structure, not on whether I put you in this bag or this bag. So it depends on X only. And that's what we're going to use. Okay, so So this is what happens in a lot of problems we work on, is that yes, you have a distribution shift, but it's on X only. Y given X doesn't change. How am I going to bind? That's the laws of physics. They don't change between the training set and the test set. Okay. And so now we're going to have to learn this distribution shift. So we have a very empirical approach where throughout the IRI system, we're going to construct representation. We're going to embed these molecules, as you can imagine, in high-dimensional space. And we're going to take an idea from Heimüller, a very beautiful idea from 2012, where according to this representation, this hidden representation that these neural networks build, we're going to try to kind of balance the two distributions so that the moment of things we care about are the same across testing and training. So we're going to learn the distribution shift not by classification, not by trying to determine whether you're in the test or calibration data. We're going to do a form of what's called entropy balancing. We're going to try to find those weights WI, which are as close, as uniform as possible, and are such that when I take key moments of representation that have been learned by your neural nets, the key features that somehow the mean difference between the test sample and the training sample is undetectable. That's how we're going to adjust for the shift. Very data-driven. So we do this. After we do this, we're going to construct p-values. And perhaps I'm going to skip the definition of these p-values. They are not p-values in the traditional sense. They are measures, they're statistical instruments, those PJs, that are going to tell me whether I should look at a drug or not. And the properties of these p-values, Pj, and I'm going to, since I'm going to run out of time, I should forego the definition of these p-values, have the property that the chance that Pj is less than alpha and you're not interested is less than alpha. So small p-values, you're probably interesting, and it's very quantifiable, but this is still marginal. All right? So we're going to take these p-values, and we're going to pass them through a selection. We're going to take those small p-values that are below a data-dependent threshold, and we're going to report this column. And now this is kind of how well this works. So these plots are very, very boring, but in a way, they are exactly the kind of stuff that make my day, if not more. And this is something that my students, they tell me, Emanuel, these plots are boring, but they tell an incredible story. I'm asking you, here's a list of drugs. How many are not what you want? What fraction are not what you want? You say, how can I know? How do I know? Like, I don't know this stuff. And yet, we said we want 25% to be not interesting, etc. And all this plot, you're going to see the red line, which is the line we produce, which is just essentially a diagram. That it somehow predicts very well. You want 25%, you get 25%. You want 30%, you get 30%. You want 10%, you get 10%. You get 50%, you get 50%. Even though you have no idea. And this is across tasks that are very different. So this one is selecting gene perturbations that will lead to high T cell proliferation. This one is going to select proteins. So this is work with genetics. Proteins with high stability, etc. And so what I want is you told me which budget you can waste. I'm going to give a list. And I want to see, no matter what budget you tell me to 20%, I want to see a straight line. And that's what you're saying. If you're not using the method that we're discussing, you're thinking you're doing great stuff. That's a blue line. That's conformal, unadapted for selection. And you see, well, you have the R through the roof. At the beginning, you're losing 75% of your money. When you think, I gave you a budget of 5%, and you're losing, your error rate is 75%. So it's a bit crazy. Okay, so we're going to see a lot of plots look like this. They're boring, but to me, they say a lot. Of course, at some point you plateau because I've discovered everything there was in the data set, and I cannot discover more. But basically, you see these straight red lines, which actually completely match the thing where I give you the budget, and we're going to deliver a set of molecules that exactly fit the budget, even though we don't know the ground truth ahead of time. All right, so time is a bit late, and I think we want to go to the party. I have many more experimental results to show you, but Maybe this is not the time to present them, so maybe I'll skip that. If you are now careful about what you do, you could either completely overshoot or miss a lot of opportunities. And so this is what these slides are trying to convey. And so it's extremely important to do the right thing. You can also answer questions like this. How many candidates can I select until I make 10% mistakes? How many candidates should I select to ensure at least 35 positive ones? So you can do things like this. You can answer questions like this. And so with confidence. So this is another scenario. I want to, how many candidates can I test until I make 20 mistakes? So all of the tools I show you can answer questions like this and says, well, if you want to make at most 20 mistakes, you can see 56 guys. And it's very close to the right answer. If you go a little bit above 56, you're going to make more than 20. And that's what this box plot is supposed to show you on the right. I'm going to give you a conservative estimate. I need to give you a lower bound on the real number. And you see again that you have the thing. I don't know how many false positives there will be, but somehow we can estimate this very well after you. Okay, so I need to wrap up. So maybe I'll say that what people in drug companies want is not only good drugs to send to their labs, but they cannot all be the same. I know this is not a popular word anymore, but we would like to select drugs that are not all the same. And so it's very important when you do selection that you have drugs that live in different parts of chemical space. And so you have to build this into your optimization and into your processing, because it's not interesting to send 20 times the same drug. So yeah, your success rate is going to be high, but that's not interesting. So you want to be able to send drugs that are quite diverse. All right, and okay, so this is what we're doing. So we can do a form of quality control for drug discovery, which I think is useful. I had more stuff about making LLMs correct, but maybe I'm going to skip that. I hope I convinced you that there's a lot of interplay between statistical thinking and AI thinking, and I think we can build better AI by taking statistical insights into account. And with that, I thank you very much for your attention.
For a great talk. I don't have a mic here. If there are questions, please, we have one over there which we cannot move. Just please approach the mic and feel free to ask your questions.
Thank you for the nice talk. So I have a question regarding the first part of the presentation, where you're talking about synthetic data and then doing additional pre-training. So how to make sure the gain with that synthetic data fine-tuning is not coming from just sharpening of the distribution, and it is actually coming because of the quality of this synthetic data?
Are we talking about the first part, about pre-training?
Yes, yes.
Okay, so the question is, how do I make sure that this data has some quality to it? Is that what you're asking me?
Yes, yes. Or in other words, why it is not just generating which it has seen in the training, and therefore like additional findings?
Well, it has seen a lot of stuff in the training, otherwise it would not be able to synthesize stuff. But it's giving you, it's presenting data that makes it easier for the model that you're going to use later to learn. So it's just presenting data in a different way. So when you go through this step, for example, the bootstrap pre-training, you generate new data. Now you're right that sometimes we have to be careful about what we do. What we check is, of course, then we use LLM. Typically, we use LLM as judges because it could be that the synthetic data we create generate hallucinations and so on. So you have to be a bit careful with this stuff. But the point of this is to actually present to you a new data set then amenable to efficient learning. And that's what seems to happen. Otherwise, I would not see the kind of performance. I would not be able to explain what we see empirically. So you basically generate data that seems to be useful. Now, it's not as useful as original data, because that's what you see at the beginning of this curve. But then it has some usefulness. And
Thank you so much.
whereas rephrasing is not that useful.
Thanks for the great talk. So in the second part, then you introduced that cost function L that was the step shape. It seemed like the threshold you had required the knowledge of the uncertainties that you had for each
Yes.
of the labels.
Yes.
So do you assume that you know the uncertainties or other ways to estimate?
But okay, so that's, I'm very glad you asked this. Because your cost function, oops, it's not the way, so.
Next. Yeah.
Your cost function is actually a random sum. And so the good thing is, like, I can estimate, so the cost function is essentially a mean, right? So it's very good to estimate a mean. And so I can give you an upper bound by, I want to say by even the central limit theorem, right? So, you know, I calculate empirically what this is, I compute the standard deviation, I multiply it by 2, that's morally right. And so then you have this upper bound. You say, but yeah, but it's only an upper bound at one point. It's not uniformly valid. And the incredible news is, yeah, but I don't need that, because the monotonicity does not, it is going to be so helpful that I don't need the upper bound to be simultaneously valid. So a lot of people actually, there is a work of Aditya Ramdas at CMU. I don't know if people know Aditya has developed extraordinary techniques based on martingale and actually ideas from Voff on martingales as betting strategies to develop super tight confidence bound on the mean of a random variable. And we use some of that, and to be honest with you, sometimes we don't. We just pretend the central limit theorem is good enough, and all this numbers that we saw, I think we use the central limit theorem, and I want 5%, I got 4.73%, so it seems to be fine. If you really want to be airtight, we're going to do, we're going to use upper bounds from Ramdas and Bobby Smith.
Thanks.
Thank you so much. But it's because it's a sum, it's an average. That's what we can do.
Any other questions?
Thanks for the very nice part. Just curious about the implication of this. The fact that we generate synthetic data from real data, and that helps improve the model. Does that imply?
You mean the part one?
Yeah, part one.
Yeah.
Does that imply the model that we're dealing with is not good enough in extracting all the knowledge that exists?
I think so. I think our hypothesis is that we are not making good use of the data we have. Like the data efficiency, so to speak, of pre-training is not, can be improved, because we can see that we can improve the quality of LLMs by essentially generating new data, which we did not have access to new data to do this. So it's, I think the thesis here is that we're not using data efficiently right now.
And I suppose one could also, if I may follow up, the scaling laws, as we know, they're experimental, empirical.
Yes, they're experimental.
They're very much model dependent as well, in that sense.
But yeah, but no matter the model you use, you typically see these things, right? So unless I'm mistaken, as the data size increases, oops, sorry, I'm going in the wrong direction. Yes, the slope might be model dependent, I agree. But this thing seems to be a lot of things, a lot of people report this, right? As I train a transformer with a certain architecture, and I give it more and more data, I'm going to see that kind of behavior. Of course, it might require, and give me more data, I might scale up the architecture a bit, but this is typically what you see. But we did not produce this plot.
Yeah, I was wondering about the thresholding of the conformal p-value. You have extremely large number of hypothetical drugs and so on, and high concentration of p-values equal to 0. So how do you really find the threshold value such that you can?
Yeah, the p-values, I don't know that they can be 0 because, okay, very good question. This is the extra term in the definition. You see there's a term in the definition. But yeah, so we're going to select p-values that are small, and then they're going to undergo a selection procedure, not unlike what you see in the multiple comparison literature, like the famous Benjamin-Hochberg procedure, and that's how we're going to adapt the selection threshold. Now, the Benjamin-Hochberg selection procedure is actually about something completely different. It's trying to estimate parameters and not testing parameters and not predicting an outcome, which is what this is. And also it requires p-values that are independent. Here, the p-values are actually quite dependent because they all use the same data set. They all depend on the calibration set I gave you. They are absolutely dependent. And that makes the math and to actually prove the results that I just gave you extremely difficult. So maybe I haven't said that, but Ying, who is a phenomenal researcher, worked extremely hard to actually be able to prove that this actually works, because it does not follow from standard statistical literature. Because the p-values all see the calibration set, so all become dependent, and what do you do then?
One last one? Yes, please.
Thank you for the enlightening talk. So my question was, and I think you have slides on this, is when you generate, in the first part, when you generate these synthetic documents, how do you ensure the factual accuracy of the synthetic?
We don't.
You don't?
But we could.
I see.
Right, so, you know, a lot of people have tools to actually, they use LLM as a judge, you can do RAGs, you can do a lot of stuff. In this work, we actually did not. But this might be a concern. In fact, if you look at the paper, I'm sorry that I glossed over this part of the presentation, maybe over all parts, but if you look at the papers, we actually report on quality metrics of the synthetic data. You know, how much of it is just pure duplication, how much of it is not factually correct, and so on. And you'll see that as the size of the training set increases from 200 to 1 trillion token, you'll see that the statistics go down, that we seem to duplicate less, we have less factuality errors, and so on. So we have 5 metrics that we carefully monitor, that are all documented in the paper, that show you a little bit what we think is the quality of the synthetic data set.
Thank you.